Intercontinental School. And our last lecturer is Professor Helmerson from Monash, and he'll be talking about BECs.
Great. Okay. Well, thank you. And so I'm going to hopefully cover a lot in these last few lectures. So I'll be primarily talking about Bose-Einstein condensation in dilute atomic gases, including some details about BEC, but also applications of BEC. I went a little long in my first two lectures going over laser cooling and trapping, so I won't actually bring up any laser cooling and trapping details in these lectures. But before I do that, I do want to take one step back to the lectures from 2 days ago. It was pointed out to me that my laser cooling history, the brief history of laser cooling, was perhaps a little too brief, and I agree, it was quite brief. I did mention that many ideas were floating around or developed since the 1970s. What I should have mentioned that there was basically two notable pioneers in the 70s. They proposed a number of techniques and a number of ideas, and this includes Letikov and Arthur Ashkin. Not only are their ideas that they proposed in the 70s still in use today, like trapping in optical lattices and dipole traps, but they also sort of shaped our thinking for the next 20 years about optical forces and the interaction of light with matter. So I just wanted to bring that up, and I've corrected my lecture notes so they're actually in there now. So let's move on to Bose-Einstein condensation. Here's a brief outline of what I'll talk about in the next two lectures, actually. I'll give you a little bit of history about BEC, some of the basic concepts associated with Bose-Einstein condensation. Then I'll discuss the experimental realization of Bose-Einstein condensation in dilute atomic gases. One of the interesting features of Bose-Einstein condensate is that it's a superfluid, and so I'll talk a little bit about that. And of course, if you're talking about superfluid, you have to talk about vortices. And then I'll talk about two applications of Bose-Einstein condensation. One has to do with using the wave nature of the atoms in something called atom optics. And then the other one, we'll talk about a new regime of Bose-Einstein condensation, the strongly correlated Bose gas. So, moving along. Here's a brief history of Bose-Einstein condensation. Basically, the idea of Bose statistics came up in 1924 from Bose, of course. And Einstein, so his original paper had to do with explaining the statistics of photons to explain Planck's black-body radiation spectrum. Einstein extended the ideas to massive particles, or atoms, in basically the same year. But in 1925, still working with these ideas of Bose-Einstein statistics, Einstein predicted that, or he saw something unusual if you looked at the statistics at low temperatures. You saw that there was actually a macroscopic population of a gas in the lowest momentum state, or the zero momentum state in this case. And then we jump ahead to basically 1995 is when people first created a Bose-Einstein condensate in a gas of atoms. It was first realized by Eric Parnell and Carl Wyman at JILA, the Joint Institute of, well, it used to be the Joint Institute of Laboratory Astrophysics, so now it's just JILA. And they realized BEC in a gas of rubidium-87 atoms. And a few months later, Wolfgang Ketterle at MIT realized Bose-Einstein condensate of gas of sodium-23 atoms. And there was a lot of progress after that, a lot of experiments, a lot of groups joining in, which resulted in the 2001 Nobel Prize in Physics being awarded to these three guys for their achievement back in 1995. This is a big jump from 1924 to 1995, so that doesn't mean there wasn't anything happening in between. In between those years, there was a lot of research on superfluid helium. And it basically involved aspects of Bose-Einstein condensation. There were a lot of powerful physics people involved in this, people like Landau in London, Onsecker, and so on. In addition to all the research in superfluid helium, there was about 20 years of research involving spin polarized hydrogen. So people were still interested in making a gas of Bose-Einstein condensate as opposed to a liquid, which is basically a strongly interacting Bose gas, if you like. And so people realized that hydrogen, spin polarized hydrogen, had some nice properties that might allow it to undergo Bose-Einstein condensation if you got to a low enough temperature. And so a number of groups were involved in this, including people like Dan Kleppner and Tom Greatek at MIT, Ike Silvera at Harvard. There was a major group in the Netherlands also involved in this kind of research. Unfortunately, after spending 20 plus years working on the system, they actually didn't achieve BEC and spin polarized hydrogen until after the atomic gases that other people were working on, laser-cooled gases. Still, a lot of their work influenced the strategies that people use with laser-cooled atoms, so it's worth mentioning. Also, if you want to, there's a very nice history of the relationship between BEC and superfluid helium on Alan Griffith's webpage. He's a professor at the University of Toronto and an old-time liquid helium theorist. So BEC, the weakly interacting atomic gas. As I mentioned, this was realized in 1995, and basically it marked the entrance of atomic physics, I think, of atomic physics moving into the realm of condensed matter physics. And as you'll see towards the end of the talk, now we seem to be strongly coupled with the condensed matter community, and it doesn't appear that there's any turning back now. A number of groups are involved in BEC research. They can be found in almost all major laboratories throughout the world. There's over 50 experimental groups. This is a number from a few years back, actually. Bose-Einstein condensates in dilute atomic gases have been realized in a number of different systems. In 1995, it was rubidium, sodium, and shortly thereafter lithium. And then that was followed by hydrogen. People finally got their Bose-Einstein condensate. But since then, there's a number of other species: potassium, cesium, metastable helium, ytterbium, chromium, and I think there might even be a few more now that have undergone Bose-Einstein condensation. In addition, you can actually get Bose-Einstein condensates of molecules, and people have demonstrated this with homonuclear diatomic molecules. BEC research, it's a very popular area. It impacts a lot of areas like, well, obviously atomic physics and also condensed matter physics, but also other areas. So here's a simple picture of Bose-Einstein condensation. It's sort of a wave picture. Quantum mechanics tells us that, of course, matter behaves like waves, with the wavelength given by the de Broglie wavelength, so it's inversely proportional to the velocity or momentum of the particles. So if you consider a collection of atoms at high temperatures, you can think of them as billiard balls basically crashing into each other. As you lower the temperature of the system, you're lowering the velocity of the atoms, and so the wavelength gets longer, and at some point you can actually begin to see some effects of the wavelength in a laboratory setting. What happens though when you get the Bose condensation temperature is that one way to think of this is the average spacing between the particles in your gas become comparable to the wavelength, and because these are boson, you can't really distinguish them. And what happens is these little particles that are now behaving like waves, they overlap and constructively interfere, and you get a buildup of a macroscopic wave. And because this is a thermodynamic process, basically you get a buildup in the lowest energy state of your system, which happens to be the ground state of your trap. And so once you cross over this transition temperature, you get this macroscopic wave in the ground state of your system, or the trap, which can often be basically a pure Bose-Einstein condensate. So basically, a Bose-Einstein condensate is a macroscopic occupation of the atoms in the lowest energy state of the system, or the trap. Why was BEC so hard to achieve for so many years, especially for people like the spin polarized hydrogen people? Well, of course, at very low temperatures, the gas wants to become a solid. At high temperatures, it's a gas. If you lower the temperature, then it either goes to solid or through liquid to solid phase. So if you actually look at the region where you want to get, where you can actually have a Bose-Einstein condensate, this is in a region that's basically forbidden if you're in the lowest energy state of the system. So you actually need a system that's metastable, not exactly in the lowest energy state. And so if you want BEC in a dilute gas, That means you have to keep the density low enough so the particles don't condense into a solid. And as a result, according to this picture, if you have, for Bose-Einstein condensation, you want the wavelength, the Broglie wavelength, to be larger than the average spacing between the atoms. So at low densities, that means you want a very large de Broglie wavelength. And the de Broglie wavelength goes inversely like the momentum, or inversely like the square root of temperature, so you want to get to low temperatures. And typically, if you want a de Broglie wavelength for a typical atom of about a micron, you need to get to a temperature of a microkelvin or less. So just to show you on this plot, because liquid helium is of course a liquid, and it's not in this forbidden region, but it's awfully close getting there. Einstein's original calculation of, or prediction of Bose-Einstein condensation had to do with the statistics of the Bose gas. Since I want to cover a lot today, I probably won't cover this in much detail, but just point out that basically you can consider some sort of potential. In this case, we'll just take a harmonic potential for simplicity. I can ask, what's the occupation number, number of particles for a given energy level, and it's given by this Bose-Einstein distribution. And so you can figure out, you can write this down and figure out what the number of particles are for an energy state for a given temperature. But what you want to do for Bose-Einstein condensation is ask how many particles are actually in the excited state. So let's forget about the ground state of the system and ask how many particles are actually in the excited state of this harmonic trap. So basically you just sum over the occupation number for all the states except the ground state, everything except the zero state there. And what this, if you do the sum correctly, you find that this sum is equal to some maximum number for a given number of particles and temperature and trap parameters, like the trap oscillation frequency. And this number is less than the total number of particles, so that means that the rest of the particles have to be somewhere, and they have to be in the ground state, or the state that you didn't count, the ground state of the trap. And that number is typically a macroscopic number. So what this means is that at some temperature, for a given number of atoms and a given trapping frequency, you're going to end up with a macroscopic occupation of number in the ground state of the system. You can use this relationship here to calculate for a given number of atoms what temperature you need for a given trap frequency. And that's just this relationship here. So if I have a given trap frequency and a given number of atoms, I can predict at what temperature will the system undergo Bose-Einstein condensation. And in this case, for the harmonic trap, I believe it just goes like T to the, it goes like N to the 1/3 here. So what you find is that basically you have essentially very few atoms in the ground state until you cross this transition temperature, and then all of a sudden you get a buildup of the number of atoms in the ground state. And by looking at the density of states in the trap, you can figure out how this population grows in the trap, and it basically grows for a harmonic trap. The number of atoms in the ground state goes like T to the 3rd power. So you find that once you cross the transition temperature, you get a rapid increase in the number of atoms in the trap. In the homogeneous case, for basically an infinite Bose gas, it goes like T to the 3 halves. So what does the ground state of the many-body system look like? What does the ground state of the particles in the trap in a Bose-Einstein condensate look like? If I had n particles. If there are no interactions, so an ideal Bose gas in a trap, then the wave function of the Bose gas is just the product of n single particle wave function. So I have a harmonic trap, I can calculate what the ground state wave function looks like. And basically the wave function of Bose-Einstein condensate is just n times that. If you have weak interactions in the system, then it's still a product of single particle wave functions, but you have to figure out what the single particle wave function looks like in the presence of weak interactions. And so what you're going to find with interactions is the wave function is slightly inflated, or looks a little bit bigger, but it's still a product, to a good approximation for weak interactions, it's just a product of n single particle wave function. When you get into the regime where you have strong interactions, which I'll mention a little towards the end of the lectures, you find that this description no longer works. It's not just a product of single particle wave functions. You have to really consider what the many-body wave function looks like when there's a large number of strong interactions or where the system's highly correlated, particles are highly correlated. So as I mentioned, you can have weak interactions in the system. What sort of weak interactions do you have? Well, for the atomic gases, they're primarily elastic two-body scattering. So I have two particles collide and scatter off of each other. If you go to higher densities, sometimes you'll see three-body processes, which usually lead to either heating or losses in the system, so it rapidly, those processes rapidly disappear. So the primary interactions in the Bose-Einstein condensate are two-body interactions. At temperatures typically less than a millikelvin, you find that these two-body interactions are essentially S-wave scattering. The atoms have such low energy that the only partial waves in the scattering process are S-wave. And the S-wave scattering is characterized by one parameter called the S-wave scattering length. So I can take into account the interactions in the Bose-Einstein condensate using a sort of a mean field approximation, parameterized basically by only one parameter, the S-wave scattering length. So a good theoretical description of the Bose condensate is that the wave function is a macroscopic wave function with an amplitude and phase. For appropriate normalization, the square of the wave function, or the square of the amplitude of the wave function, is essentially just the density of your Bose-Einstein condensate. In the weakly interaction regime, which means that the scattering length is typically much less than the average spacing between particles in your Bose-Einstein condensate, the BEC, or Bose-Einstein condensate, obeys what's called the Gross-Pitaevskii equation, which is a form of nonlinear Schrodinger equation. So you have the normal Schrodinger equation, which has a kinetic energy term. You might have a term for the trapping potential, which is typically present in these atomic Bose gases. And so that is basically the Schrodinger equation. But then you have this extra term here, which takes into account the interactions between the particles in this mean field approximation. So the interactions are parameterized by some sort of interaction constant, which I call G here. And also, it's proportional to the density of the particles. And this one parameter G, which characterizes the interaction strength of the coupling between the particles, depends essentially only on the particle's mass and on their scattering property by the S-wave scattering length. If you want to know something about the correlations between the particles, you can do some sort of linear expansion of excitations in the system, which obey the Bogoliubov equations, and you can find out what the correlations are. But because this parameter here, if you like, Na cubed, it should be cubed actually, is typically much less than 1%, the system, you don't typically have to worry about the correlations between the particles. So this is actually a very, very good description of the Bose gas for these dilute, weakly interacting systems. And so a lot of the papers you read are basically solving this equation in various situations, and it describes most of the experiments quite well. One convenient approximation when talking about Bose, weakly interacting Bose-Einstein condensates is they call the Thomas-Fermi approximation. So you can start from the Gross-Pitaevskii equation and predict what the shape of the Bose-Einstein condensate is going to be based on this Thomas-Fermi approximation. Typically in the BEC, this kinetic energy term is much less than the interaction term. And so you can usually neglect the kinetic energy term in the Thomas-Fermi approximation. In fact, that's what the Thomas-Fermi approximation is. And then you just end up with this equation for your Gross-Pitaevskii equation if I neglect the kinetic energy term. And you can just invert that and solve for the square of the wave function or the density. And you find that basically the density profile only depends on the shape of the trap. So the density profile of the BEC is given by the shape of the trap. And typically condensates are made in harmonic potentials, harmonic-shaped traps. So if you consider a harmonic-shaped trap, then of course the density profile is just going to be an inverted parabola. So it looks like an inverted parabola. People often characterize the size of their BECs by something they call the Thomas-Fermi radius, which is essentially the radius of this or half the diameter of this inverted parabola. So here's an example of for a typical atom that people use in Bose-Einstein condensates. If I consider 1,000,000 atoms in my Bose-Einstein condensate of rubidium, and I know the S-wave scattering length for the system, if I put that in a harmonic trap at a 20 hertz frequency, then this is the type of distribution you're going to get based on the Thomas-Fermi approximation. So it's an inverted parabola. If I just look at what the ground state of this 20 hertz trap is, the wave function associated with that is this harmonic or this Gaussian shaped wave function here. So clearly the interactions of the atoms basically blow the size of this wave function up quite a bit. And you can see that this is so much larger than the width of this that it was a good approximation to neglect the kinetic energy of the system. Here's this, another picture showing another harmonic trap. This is the ground state wave function associated with the trap. And here's some data points for showing a measurement of the density distribution in a real BEC. And so you can see that, again, the real BEC is much bigger than the ground state wave function in the system. And for most of the cloud, it's fit by this inverted parabola having to do with the shape of the harmonic trap. Of course, you'll notice here that in the wings, it doesn't fit very well. And that's because when you get to low enough density, of course, you can't neglect the kinetic energy term anymore. And so you're going to have to actually do a full calculation of the Gross-Pitaevskii equation if you want to know what the shape of the Bose-Einstein condensate is out there. And typically, you can predict sort of what the scale length of, or how fast this is going to fall off. And it's given by something called the correlation or healing length of the system, which goes like inversely like the square root of density, and it depends on the strength of the interactions in the system. One way to think of it is if I have a wave function, how rapidly can I basically bend or distort the wave function over what sort of length scale can I do that? And that's going to depend on how strong the interactions are in the system. And so that parameter, which characterizes how sharply I can bend the wave function, is the healing length. So how to make an atomic Bose gas? Well, I described all the techniques in my first two lectures, so I won't do anything more than just put up this one slide here. It's basically, nowadays, it's basically 3 easy steps. You start with a collection of laser-cooled atoms. You collect them usually in a magneto-optic trap, and then you transfer them into some sort of static potential. It's usually either a magnetic trap or it's an optical dipole trap. You want some sort of potential where the atoms are not heated while they're in the system. And then you perform the process of evaporative cooling. You selectively remove the hot atoms from the system. The cloud in the trap, by collisions, the cloud rethermalizes to a new temperature, which is lower because you remove the hot atoms of the system. And eventually what happens is you get to a low enough temperature and a high enough density that you cross this BEC transition. So here's sort of a typical trajectory in phase space for how to get the Bose-Einstein condensate. You start with your atoms, either you have to collect them from a room temperature vapor or maybe some other source slightly hotter, but you use laser cooling to go several orders of magnitude down in phase space, or up, actually up in phase space density, or down in temperature. Excuse me. But at some point, you can't actually use laser cooling anymore. It usually shuts off due to some sort of collision process involving excited state atoms or some other process, reabsorption of photon process. And so then you have to switch to this evaporative cooling, and then you put the atoms in their static trap, and you do the evaporative cooling, and that takes you the rest of the way to Bose-Einstein condensation. And typically that occurs at just under a microkelvin for densities on the order of about 10 to 14 or 15 atoms per cubic centimeter. So here's the images that were published on the first Bose-Einstein condensate created in rubidium, 87, back in 1995. They saw that in their case the transition temperature was somewhere around 200 nanokelvin. And what they saw is a rise in the density distribution of the atoms as they piled up in the ground state of the trap. So this was a monumental achievement led in this case by the laser cooling community, and it's one of the the major triumphs of, I think, of all the work that went into developing laser cooling and trapping over 20-some years. But you can't forget to mention that a lot of the work that went into in studies of spin polarized hydrogen were actually leveraged to get here. In fact, the whole idea of evaporative cooling comes from the spin polarized hydrogen community. They developed the idea of evaporative cooling, and it was successfully applied to the laser-cooled atoms to get the BEC. What are some typical numbers for BECs? Typically, you make your condensates between maybe 1,000 well, people have made Bose-Einstein condensates of alkali atoms up to 10 to the 8 atoms. The spin polarized hydrogen people have gone a little bit higher. But the typical BECs are usually about 10 to the 5 or 10 to the 6 atoms. The densities are in the range of about 10 to the 13 to 10 to the 15. Usually if you try to go to higher densities, these three-body collisions and other bad processes start destroying your condensate. The characteristic size, because of the interactions of the atoms, blows the wave function up. The characteristic size of your BEC is typically on the order of tens of microns. And the temperatures are in the range of just under a microkelvin all the way down to 50 nanokelvin. In fact, people have gotten Bose condensates down below a nanokelvin, but usually that's not what they're created. Number of atoms in the Bose condensate can be quite high, the fraction of atoms. Usually greater, you can get BECs where you get greater than 95% of the atoms in the ground state of the system. And it's hard to actually measure above this level. This is in contrast to liquid helium, which is a strongly interacting system, so the actual amount of atoms that are in the lowest energy state, in the case of helium, would be like the zero momentum state. That's typically on the order of, I think, somewhere around 10 or 15% for liquid helium because it's such a strongly interacting system. The type of energies, the chemical potential, or the sort of the energy scale of your condensate is typically on the order of 20 to 200 nanokelvin. So this is sort of the energy associated with your condensate, even though the temperature, transition temperature may be higher than the temperature of the system. This has to do with basically the amount of energy associated with the interaction of your condensate. And because it's a bulk material, it's a gas, you can determine what the speed of sound in the system is, and that's on the order of a few millimeters per second, which is typically much less than a liquid like liquid helium, which is meters per second. And then this coherence length that we measure that determines how rapidly you can bend the wave function, that's typically on the order of about some fraction of a micron in a Bose-Einstein condensate. But that's much longer than helium. Helium is on the order of angstrom type scale for that. How do we actually probe a Bose-Einstein condensate? Well, typically, the most popular way is to take some sort of picture of the cloud. And the technique that most people use is something called absorption imaging. In fact, that was the technique first used to image the first Bose-Einstein condensate. And it's exactly what it sounds like. You have your cloud of atoms here, and you send a laser beam in that's resonant with the excitation energy of the atoms. So the atoms want to scatter light out of this beam. And what they do is basically create a shadow in your beam, because they're scattering light out, and you image this shadow onto a CCD panel. Now, the amount of light that it scatters depends on the density and also the cross-section for scattering. And so it's going to, the amount of light scattered out is going to depend on the number of atoms that the light sees as it propagates along. And so typically it obeys some sort of Beer's law for absorption as a function of length. And so as a result, what you see here is basically the integrated density profile along the propagation direction of the beam. This technique, of course, because you're scattering photons, is destructive, so it destroys the condensate. So typically, after you take a picture, you have to make another Bose-Einstein condensate and repeat your experiment. Yeah. You take another picture. There are techniques to actually take pictures of BECs without completely destroying them. And they rely on phase contrast techniques, where you have some sort of phase shift of the light passing through the Bose-Einstein condensate. And so here's some, one of the earliest demonstrations of this came out of Wolfgang Ketterle's group, where they used a phase plate, appropriate phase plate to do phase contrast images. And here you can see they can take a series of pictures of their elongated shaped Bose-Einstein condensate, and from image to image it looks like it hasn't changed very much in density, which means that there's sort of minimal absorption. Of course, you're going to have some absorption. The Kronig relation tells you if you're observing some sort of phase shift through the system, then you have to have a little bit of absorption associated with it. But typically that can be kept quite low, so you can take multiple images. Here's a nice series of images on one cloud that they've taken where they actually form the Bose condensate. So here's the thermal cloud, and as they lower the temperature of the system by rapid cooling, you can see that the condensate eventually forms, and you get almost a pure BEC. The other thing people typically do is they measure the momentum distribution of the BEC, and that can be done by a technique called time-of-flight imaging. So you have your Bose-Einstein condensate. It's basically stationary, but it has some momentum with it to it because it has a finite size by the Heisenberg uncertainty relationship. That means it has to have some momentum spread. And so if you release the cloud from your trap, then it's going to start expanding due to this momentum spread. And so if you take a picture sometime later, you find that it's bigger, and by knowing the time between when you released the atoms and when you took the picture, you can find out what the momentum spread of the cloud is. You can equate that to the momentum spread. Alternatively, if you don't do an experiment where you give the atoms a kick or something, or transfer momentum to them, you'll find that after some time they've moved to a new location by measuring the distance that they've moved over the time between when you applied the momentum and when you took the picture. You can figure out what their linear momentum is. So you can measure both the momentum spread and the center of mass momentum of the atomic cloud using this time-of-flight technique. So one of the, as I mentioned, one of the interesting things about a Bose-Einstein condensate is that it's a superfluid. And so let me just briefly remind you about some concepts of superfluidity. If you look in Leggett's book on quantum liquids, early on in the introductory chapter, he mentions that there's basically two universally accepted premises about superfluidity. One is that superconductivity and superfluidity are essentially the same thing. Superconductivity just happens to occur in a charged system, and superfluidity is in a neutral system, but it's basically the phenomena are basically the same, and the underlying mechanism is usually Bose-Einstein condensation. And so that's the second accepted premise, is that the underlying mechanism in this system is usually BEC. In the case where you have fermions like electrons, then what happens is you have a process like pairing of electrons, like Cooper pairing in a superconductor, that results in a composite particle that behaves like a boson, and then it can undergo Bose-Einstein condensation. In addition, superfluidity and also superconductivity is not really a single phenomenon, but actually a complex or a suite of phenomena that normally occur in conjunction. And so a lot of times when people talk about superfluidity, they're usually referring to one sort of phenomenon that occurs in the superfluid. And that's sometimes makes it a little bit difficult to define exactly what a superfluid is. Because a superfluid exhibits a number of different phenomena that a normal fluid doesn't exhibit. One of the phenomena that it exhibits is non-classical rotational inertia, which is related to the irrotational flow. So typically a superfluid is irrotational. You can see quantized vortices in superfluid. Exhibits second sound. There's something called thermal counterflow, which has to do with the relative motion between the thermal component and the superfluid. There's the famous fountain effect, dissipationless flow, or friction, persistent currents. For example, in the superconducting loop, if you start a current going around, it basically flows forever. So superfluidity was discovered in helium, was discovered by Allen and Wiesner and Kapitsa, and then London, I think, was the first person to introduce the idea that superfluidity might be related to BEC. So, in the list here, I mentioned that one of the things that you often observe in the superfluid is irrotational flow in quantized vortices. This is pretty easy to see if you look at the equation, especially in the Bose-Einstein condensate, where basically the superfluid, or the Bose-Einstein condensate, is described by this macroscopic wave function, characterized by an amplitude and a phase. The velocity of the atoms of the superfluid is, you can determine from the gradient of the phase. So as a result, if you look at, take the curl of the velocity, because it's the gradient of the phase, the curl of the velocity is 0 around any point. And hence, this tells you that the superfluid is irrotational. You can't really rotate a superfluid. But it's possible for a superfluid to exhibit rigid body rotation, or something that looks like rigid body rotation. And this occurs above a certain critical velocity. So if you're trying to spin the superfluid at a very low velocity, below the critical velocity or the critical rotation rate, you'll find that the superfluid doesn't want to rotate. And so this is this concept of non-classical rotational inertia. Above this critical rotation speed, you find that the system actually will undergo rigid body rotation, or what looks like rigid body rotation. But the way it occurs is, because the superfluid still has to be irrotational, is that you have quantized vortices in the system. And when you have a vortex in the system, it turns out that it still has to be irrotational, and you still have to satisfy this condition. But along the vortex, which is a singularity, if you integrate around that vortex, then it just has to be the wave function just has to be continuous going around. And so you find that basically the vortices have to be quantized. And if you have a collection of vortices and you integrate around all the vortices, you can have a net rotation, something that looks like a net rotation. And so this was proposed by both Onsager and Feynman to explain sort of the behavior of the superfluid, that there would be these quantized vortices in the system. Gross and Pitaevskii were the first to, I think, calculate what the shape of the vortex would look like when they put forth the Gross-Pitaevskii equation. And it looks, the vortex basically behaves, goes like 1 over the distance from the core of the vortex. But the size of the vortex is if you solve the Gross-Pitaevskii equation, you'll find that the characteristic size of the core in the vortex is given by the healing length here. In other words, it's how quickly you can bend the wave function, and in this case take it to 0, will be determined by the healing length. So how do people actually generate vortices in Bose-Einstein condensates? Typically, the easiest way to do this is to stir up the condensate. So there's a number of different techniques. You can even transfer orbital angular momentum of light to the atoms to generate a vortex. But probably the most popular way is to take your atoms in your trap, distort your trap somehow, and then rotate the trap around. And one way to distort the trap is to put dipole potentials, like two dipole lasers, on the edge, so it makes the trap a little bit wider, and then you can rotate these laser beams around. And this was used by the group led by Jean Balibar, the École Normale, and they were able to demonstrate generation of quantized vortices this way, and I'll show you some images in a minute. Which brings me to how do you actually image these vortices. As I mentioned, the core in the vortex is going to be on the order of the healing length, and for typical densities and atoms that you work with, the size of the core is some fraction of a micron. And now you're shining light on these systems that's on the order of a micron, so these cores have a diameter that's typically less than the wavelength of light that you're using to image. So basically you won't be able to see them very well, if at all. But what's nice is that if I release the Bose-Einstein condensate from the trap and it expands, so does the core. And after some time of flight expansion of the cloud, the core becomes big enough that I can actually image it with light. And so if you start with a core that's sub-micron, after the cloud expands out, you can get to something that's on size scale of a few microns. And so when I use light to image it, I can actually see it. And here's an image of a Bose-Einstein condensate with a vortex in it. You can clearly see the vortex core. This is after the cloud is expanded by time of flare. So as I mentioned, the group in Paris, led by Jean Gallivan, were the first to actually generate, well, they weren't the first persons to generate a vortex. That was done by Eric Parnell's group using the phase engineering technique. But the group in ENS was the first one to actually stir up the condensate and generate vortices. And what they saw is that before stirring, they just had their normal BEC. But after they stirred the cloud around for a while, rotated the cloud around to get it spinning, then they saw the presence of these quantized vortices. And since then, people have used a similar technique to really rotate up big clouds. And in Wolfgang Ketterle's group at MIT, they've generated clouds where they've seen up to 300 vortices in the system. You'll notice that the vortices arrange themselves in a nice pattern, in this case, in sort of this triangular lattice pattern called the Abrikosov lattice. And that's because the vortices actually repel each other. If you calculate what the fluid field is around the vortex, it's spinning around. But if you look at what the resulting fluid field is from two vortices, you find that if you look at the total fluid pattern, it effectively looks like a repulsion between the vortices. And so they arrange themselves in this nice lattice structure, which happens to be triangular. BECs can be made in a wide variety of shapes. Atomic BECs have been created in different shapes and sizes: spherical, pancake, very oblate, cigar shaped, very long, even ring shaped. You can also squish down one dimension very tightly, or even two dimensions very tightly, to create effectively reduced dimensionality BECs. So you can have your 3D BEC and you can squish down one dimension of your trap so tight that the atoms are localized to the ground state in the tight direction. So basically the wave function of the atoms in the tight direction look like the single particle wave function in that tight direction. And then basically what you've done is basically frozen all the dynamics out. If this is tight enough, then any sorts of things that are happening in the cloud can excite any motion in the tight direction. And so you consider the direction to be frozen out. And in this way, people have made 2D BECs. If you squish down two dimensions, you get 1D BECs. So, I'm getting close to break, is that right? Okay, so let me just bring up one more thing of superfluidity, because it's something I happen to work on. As I mentioned, you can make BECs in ring-shaped traps, and one aspect of superfluidity that was very interesting in helium and also in superconductors is persistent flow. If I have a superconducting loop and I start a current in it, it basically flows forever. Same thing with liquid helium. If I have a toroidal-shaped container and I have liquid helium, superfluid helium flowing around, that will basically flow indefinitely. And so we were interested in doing similar experiments in gas, in a Bose-Einstein condensate. So we developed a toroidal-shaped trap, a trap that has this sort of Mexican hat-shaped potential. And the way we did is we took our normal harmonic trap and we put a dipole beam in the middle that repelled atoms. And so then, as long as the height of this barrier in the middle is more than the chemical potential associated with your BEC, you're going to have a ring-shaped Bose-Einstein condensate. And so that's an image of our cloud in this trap. It looks like a donut. And then, I don't have time to talk about this, but we actually use, rather than stir up the trap, we use orbital angular momentum of light and transferred that to the atoms in the cloud and got them spinning around the trap. And what we saw in that situation is that if you have the atoms spinning, you get them flowing around in the trap, this flow seems to persist for much longer than if you just had them in a normal harmonic trap. So if I have them in a harmonic trap and I transfer angular momentum and generate a vortex in the system, we find that the vortex leaves after about half a second due to some loss mechanism. But if I have it in this toroidal-shaped trap, or this ring-shaped trap, and I start the atoms flowing around, it survives much longer, in this case out to about 10 seconds. And we've since then improved the experiment, and so we have persistent currents now above 40 seconds. So this was one of the first examples of demonstrating persistent currents in the dilute Bose gas. So actually this would be a good place to stop, and then I can pick up on my second lecture where I'll talk about two different applications of Bose-Einstein condensates. Thanks.
Thank you, Chris.
All optical is a bit of a misnomer. You can use only optical trap, but you still have to do the evaporative cooling. Okay. Nobody's actually used only laser cooling to get the BEC. The closest they've come is like within a factor of 3 or 5 in space distance. It's a real tough problem.
You can do the dipole trap.
But you can do the dipole trap, and that's very popular. It's a lot more popular. I mean, initially people, the initial experiments only produced fairly small condensates, 1,000, 10,000 atoms. But now people routinely make 10 to 5 atom in dipole trap, so it's a much more popular technique.
Any other questions? Alex?
With the vortex, the critical velocity in the fluid rotation,
Right.
is there some way you can spin it and have the correlation just completely disappear from the system, like phase transition?
Yeah. So there's that angular velocity is just to get a vortex in the system. So if you spin it above that critical angular velocity, then in some sense you've allowed, it's equivalent to having enough phase winding around the wave function to get a vortex in. If you spin it really fast, what happens is you get, if the fluid velocity is considerably higher, you exceed another critical velocity, which is the breakdown of the superfluidity. And so that's it's usually called the superfluid critical velocity. And that's typically in these experiments probably a factor of 20 to 100 times higher. However, nobody really knows exactly what it is. There are predictions that it could be, there's something called the Landau critical velocity, which has to do with when you're allowed to scatter off of particles in the system. Because you have to have some sort of, if you're going to destroy the superfluidity, you have to have some dissipation mechanism. And so that's sort of the critical velocity to get dissipation in the system. But nobody's actually measured that. In fact, that's one of the reasons we started these ring BEC experiments, is to try to measure that. And so that's what they're doing now in the labs.
And another question about the size of the BEC. When you get it down to the point where it transitions into a BEC, what's the typical size in it?
About 10 microns.
Any question?
So have Goldstone modes been observed in BEC?
Depends on how you want to think about it, I guess. I mean, you can describe the BEC transition as spontaneous symmetry breaking. I guess technically, no, I don't think they've observed the Goldstone.